Now we're going to move to confidence interval estimates, but first a story to kind of set this up. So I kind of mentioned this earlier, but back in the 1800s, Guinness Brewery was a small local brewery looking to expand their operations from what we would call today basically a craft brewery into an industrial brewery where they're putting out large amounts of beer. So taste testing small batches of beer was easy enough, but when they wanted to move to an industrial scale, they needed to find a way to test large batches for quality and to be confident that those samples that they were testing were representative of all that beer. Their head brewer was a chemist and a mathematician named William Gossett. So sure, you can drink gallons of beer from each bat to make sure that each one tastes good. But one person couldn't possibly drink all that. And even if they could at an industrial brewery, they probably wouldn't be able to write down their thoughts or even speak in complete sentences. So you need a large sample because if you draw a cup of beer from the top of the vat, it may not be an accurate assessment. Think if heavier stuff starts to settle, you may have more watered down beer on top and heavier, thicker beer on the bottom. So you need to sample from all over the place in order to get a real accurate sample, which means a large sample size. So what William Gossett faced was a statistical question, was how can I use a small sample size to get an accurate estimate of the population mean? When we put it this way, it's a lot more boring, but it's also something that we have the tools to answer. And we have some of these tools specifically thanks to William Gossett and his work. So we won't be talking about the test that he specifically designed, the student's T curve, but we will talk about the basic problem and then use some of the student's T. Any sample mean that you estimate is likely to differ from the actual population mean, even if they're close to each other. Even if we do a good job, they're probably not going to be perfect. So we calculate what we call confidence intervals, where we are confident that the mean falls within the range of a certain level of probability. So we can say a confidence interval is a range of values that likely contain the true value of a population parameter. It provides a measure of uncertainty around that point estimated from the sampled data. So you make an assumption about a population, and then, or sometimes we call that a hypothesis, and then we test that hypothesis with sample data. So the result will be something like this. The 95% confidence interval is the mean of 23.5 plus or minus 4.32. So we give the confidence level. It's usually 90, 95, or 99, the mean, and then a range above and below. So in rare cases, we have the population standard deviation. Um, this is basically only done when we have, basically exercises for courses, but it makes the math just a little bit simpler. So we typically cover that first. So we have mu or the population mean right here in the middle. This is the mean that I talked about in the example. X bar is the sample mean. Z represents the value of Z scores at level alpha. So we might say the 10% level, meaning 90%. Or we say the alpha is at the 5% level, which corresponds to a 95% confidence interval. Now note here that it says alpha divided by 2, or appears to say alpha divided by 2. This doesn't mean that you divide the number by 2. Instead, what it means is that our confidence interval is two-sided. We care about, we're testing for the difference above the mean and below the mean. So when you look for the z-score in the table, make sure you look under the two-sided test instead of a one-sided test. That's what that 2 tells you. And then sigma divided by the square root of n is the standard error of the mean. So let's walk through a quick example. Let's say that we wanted to calculate the 95% confidence level of the mean for the approval rating of President Obama in a population where the sample mean is 56%. And the standard deviation is, population standard deviation is 12.1, the sample size of 500. Well, you can plug these right into that formula. And you have on this side, you have the X bar, so the sample mean minus all this. On the other side, you have it plus all that. So this will spit out the number that's less than the mean, the one that's greater than the mean. So when you plug those in, you put in 56 for X bar. You look at the Z table, where alpha is 0.95, and it's a two-sided test. The 95 here, the 2 means the two-sided test, remember? The z-score is 1.96. When you work with these a lot and you work with the 90, 95, and 99% confidence interval with two-sided tests, you remember 1.96, 1.65, like that. Um, you begin to memorize them because you use them so frequently. Then here, the 12.1 divided by the square root of 500. So that's the population standard deviation and sample size. On the other side of the mu, we have the exact same thing, only this is plus, and that side is minus. So when we do algebra, we work out the math, we get a 95% confidence interval with a mean equals 56 plus or minus 1.06. Now, unfortunately, in the real world, we rarely know the population standard deviation. That's basically just what we'll see in exercises. But when this is the case, we have to do something slightly different. You can see here that the formula, although it's different, has the same basic properties. We have the mu in the middle, the population mean. We have the sample mean, x bar, here on each side. On the left side, less than the population mean, we have minus all this. On the right side, we have plus all that. That'll be greater than the population mean. So mu in the center, x bar again. Here, the difference, instead of the z-score, here we have the t-score. So here we'll use the t table instead of the z table. And this is one of the things that comes to us from William Gossett. So now we have n minus 1 here times s divided by n, or the sample standard deviation divided by the size of the sample, the square root of the size of the sample. So if we wanted to do a similar problem, say we have a 95% confidence interval, what is the mean for the approval rating of President Obama? Again, where the population, or where the sample mean is 56%, the sample standard deviation is 65.3, and the sample size is 1,025. Again, we plug all these numbers in. We go to the t-table and we find that value of the 95% confidence interval. In this case, it's 1.96 again. On this side, it's the mean 56 minus all this. On the right side, it's the sample mean 56 plus all this. When we do the algebra and work it out, we get a mean of 56 plus or minus 4.0.